Hello and welcome back to Haskell for Dilettantes. The channel is Tea Leaves Programming, and we're programming like it's 1979. Or actually a little later than 1979, because Haskell did not exist back then. We were in the middle of doing the applicative chapter or part of the Data 61/System FP course. System F, I think. So we had just finished implementing our type classes, and now we want to use our type class. And our first full exercise is lift 2. Apply a binary function in the environment. Environment here refers to the, I'm just going to say it, container. I know someone is screaming every time I say that. But if you have something in a list, then the list is the environment. If you have an int inside an optional, then the optional is the environment. So our example here is lift 2, and then our function is plus, which is indeed a binary function, takes 2 arguments. And then we have exactly 1, 7, exactly 1, 8. 7 plus 8 is 15. So in our traditional way of doing this, we would be saying 7 plus 8. But we don't have 7 plus 8. We have exactly 1. Yikes. 7 and exactly 1, 8. And so the question is, how do you add these things? And the answer is you kind of don't, right? Adding exactly ones is not a supported operation, but what is supported is this idea of lifting a function from outside into this operation. And so we're going to somehow lift this thing and apply it to both of those. And the word lift is it's the best word that I know of to describe this. It has all of these connotations that don't quite apply. Anyway, so we could look at some other examples here. If we lift plus into a list context, 1, 2, 3, and then 4, 5, we end up with a single list. 5, 6, 6, 7, 7, 8. And that's because, right, 1 plus 4 is 5, 1 plus 5 is 6, then 2 plus 4 is 6, 2 plus 5 is 7, 3 plus 4 is 7, and 3 plus 5 is 8. So that's a little bit confusing there, right? The lists are kind of multiplying themselves out. And this is one of the things about applicative that I find a little bit confusing. This one is fairly straightforward, full 7, full 8. So I think the operation here that is kind of implicit, right? We were talking about lifting a function. We're almost lifting 2 functions. I don't know if a second function is the way to describe it, but these arguments are combining in a way that I would call, and here's a $10 category theory word, monoidal. The monoidal operation is if you have 2 things and you squish them together. That's my scientific description of it. You're squishing them together. If we squish together 2 full things, we get a third full thing without regards to what happens to the item here. If we squish 2 lists together, right? Like one could say squishing these lists should result in 5 items, but actually we're ending up with 6. And the reason for that is we're essentially multiplying these lists together. It's like a product operation. So this gives us a lot to go on here. So here's our type signature, where K is an applicative. We have a function from A to B to C. That is a binary function, takes 2 arguments, returns a third argument. And we have 2 items in the environment, as we just said. So I don't actually know how to implement this. let's just bind some names here and look at what the types tell us. And I expect this to literally just be reiterating the type signature. But I like to do that just to make sure that I'm understanding things correctly. Okay, our whole is of the type we want returned. And these are the things we just bounded to. All of our type class efforts in the last exercise were about implementing this apply operator. So logic suggests to me that maybe that apply operator is somehow relevant here. So what does that look like? Well, we have these two things, Ka and Kb. And maybe we could apply those to each other, right? Because they've got the right type, and that's what the apply operator does. Give it a function from A to B, and an A return a B. So that's wrong because we know that our Ka, we know this is wrong because Ka is not a thing of functions. And I'm sure we'll get a very dramatic type error. Right, expected some K, that's a function. So this function is in the context K. It's not in the context. So we need to get it into the context, and that feels like that's a functorial operation, right? To put this non-K function into this context K is functorial. So let's use map to do that. Still think this is not right? Compiled, that's interesting. Let's take our complicated example here and try it. I'm not ready to move on. We got the right answer, but I'm unhappy with how we got here. What happens if we put a hole here? It's just going to say Ka, isn't it? Found our hole of type Ka. A to B to C, and then there's an A and a B yielding a C. I guess that makes sense. Can we do something crazy here? This might not work out, and I apologize if this is if this turns out to be a red herring. What if we do this? KFN where KFN is equal to will that even work? Like, what I'm trying to do is get a binding that shows me this thing is in the environment. That would satisfy me. Nope. Doesn't like that. Is there anything else I can do? Well, what if I did this? Right, that satisfy the syntax? Let's see. Okay, great. So this is closer to what I wanted to see. So we still have our whole Ka because we just threw that there to make this, to get this error message back. And here we have KFN, which wants a Ka and will yield a K of B to C. So then from here, oops, I went to the wrong file. From here, we can just, if we put Ka here and then apply that to KB, that should work. Keep going to the wrong buffer. Okay, so this is not the optimal implementation, but I liked doing this because it makes it more clear to me how this thing got into the environment, because I could use the compiler to inspect the types. Well, let's do it for real, and let's do it the right way. And so this looks like KA, KB. All right. Apply a ternary function in the environment. Can be written using lift2 and apply. We have a lot of examples here. And note here how if there's any empties in our optional examples, they yield empty. That is the monoidal behavior of an optional. And I know I said monoid, and a lot of you are thinking monad. No, monoids are different than monads. I think something a lot of Haskell people wonder is how much category theory is it worth learning? I'm not a Haskell professional, so someone who does it for a living surely has a different opinion. As a dilettante, I would say learn as little as you possibly can. Learn only the amount you need, because it's a very deep hole. All right, so lift 3. So what happens if we implement this without lift 2 and apply? Like, what if we just do will that work? Seems to work. Let's try an example. Let's do one of our optionals. 7 plus 8 plus 9 is 24. All right, so that's one implementation. But they do tell us it can be implemented with lift 2 and apply. So what would that look like? Lift 2, function k, kb, kc equals lift 2, function k, kb. I'm guessing here, but this feels right to me, right? We're just smacking an apply onto the end. Nope. Multiple declarations of lift 2. Oh, that's pretty silly. Great. And that worked. So 2 different implementations here. We just do it with this pattern of functor apply, apply, or using lift 2 and tacking on an extra apply. Well, now we can see they're going to really drive the point home and have us implement more of these. So let's go ahead and we'll implement these with our previous version of lift. Actually, this is maybe a good example of where we could do point free, right? So we could do this like so. No. 4 arguments, quaternary. That'll work. Why not? Oh, because I put an extra argument here. I could do this, right? But what if we left off that last argument and did that? Will that work? I think this is the same thing that I think the same thing will happen that happened when I tried to pull out that functor, that map operation. I think this is going to be a syntax error, but if we do this, and I'm going to take time to explain this a little bit, if it works. If it doesn't work, maybe I'll cut it out of the video and pretend it never happened. Okay, couldn't match type A. Might need some parentheses here. Okay, so what in the Sam Hill is going on here? This is actually a clever variant of point-free programming. So lift4 takes 5 arguments, a function, and 4 items in the context. I've only given it 4 arguments here, this function and 3 items in the context. And then I know that I'm going to be applying this to whatever comes next. So we simply didn't give whatever comes next a name. We just left it off. And when this is used, when lift4 is used in anger, there will be another argument, and that is kind of implicitly right here. And I think, will that actually, I don't think that's going to give me anything useful, right? No, actually, well, that's great. The whole actually shows us that it's expecting some value KD, and that value is going to be provided by the caller. Lift0, apply a nullery function in the environment. What does that mean? A nullery function. What even is a nullery function? A nullery function is a function that takes 0 arguments. Well, if a function takes 0 arguments, it must always return the same value by definition, because it wouldn't be a true function, a mathematical function, if it returned a different value. Okay, well, let's follow the types here. We're going to get a KA back. This is just going to say KA. I don't even know why I'm bothering. Yeah, I found a whole KA. Lift0, that's ourselves, function. Constraints include applicative K. So how do we get, so we're being given an item, and we want to get back an item in the environment. We have a function to do that. If we go back to the in fact, I'm disappointed, if I'm right about this, I'm disappointed that I'm not getting a compiler hint for this. Maybe I'm wrong. But if we go back, there are these 2 functions, pure and apply. And pure takes an A and returns a KA. I think it's just, in fact, I'm declaring lift0 is a synonym for pure. We don't even need to bind a name here. Yeah. Lift05. Oh, it has to be in that context. That's why. So can I come up with an example without looking at their examples? How about lift2 plus exactly 1, 6. So that's our context. And then pure 8. Will that work? And that works. So this pure pulls it into the existing context. It's a bit confusing, if I'm honest. Apply a unary function in the environment can be written using lift0 and apply. All right, well, let's think about that. We have a function and we have something in our context. We want to get that function applied to the thing in the context. So I could just lift that function and apply it to KA. And the reason this works here is that the fact that we're giving this argument provides the necessary context. I'm going to be really embarrassed if this doesn't work. Seems like it worked. Let's try an example. All right. Apply discarding the value of the first argument. Pronounced right apply. Right apply. Okay. So if we have a list 1, 2, 3, right applied to a list 4, 5, 6, we get back 456, 456, 456. What? This one makes a little more sense to me. Full 7, right applied to full 8 gives you full 8. Well, they're discarding that environment. But again, it's this monoidal, right? 2 times 3 is 6, so there's 6 here. 3 times 3 is 9. So that's pretty much the same, except for... So let's talk a little more about monoids. How do we know? What does it mean to discard the first argument in this context? Like, I could imagine a world where instead of 456, 456, 456, I got something like 16, 20, 24, 20, 25, 30, if you see what I'm saying, right? Like, why isn't this kind of being applied to itself? To give you, let me reify that example, all right? 5, 6, nil. Why am I not copying and pasting? If I did that, that's the sort of thing we would get. 4 times 4 is 16, 4 times 5 is 20, yada, yada, yada. Why this? And the answer is that the slots for these items, the context is still there. So, but the actual value is not there. So what value is there? And the answer, I believe, is whatever the monoidal identity is. So in the case of multiplication, the monoidal identity is 1. And so kind of implicitly, this list is going to be 1, 1, 1, which if we actually fed that in, that's what we would get, right? If we did that here, let's try that out. Let's do a 1, 1, 1, and 4, 5, 6, right? Well, because I'm doing a plus, but if I did a multiplication, right, that's what right apply ends up kind of looking like. So that doesn't actually help me. All of that said, that doesn't actually help me implement it. So we have some KA and some KB, and we're going to return KB. That's interesting, isn't it? So we've got some KA, and we know that's going to be thrown away. So probably this is going to look very different. We're getting back some whole. KB, K and B are rigid type variables. Okay, so my first question is, why isn't that a valid solution to this? I think the answer might be this is a type checking solution. This'll type check, but it won't actually function the way we want. Let me see if I'm right that it type checks. It does. But if we actually run the use case, like so, this is just going to return 456, which is not what we want this to do. So this is one of the first instances in this course where we're following the types doesn't get us to the answer. You could imagine pathological cases where you abuse the identity function to force things to work. But this is good. I like this. So now we actually have to think about what does it mean to apply this to itself. Or rather to apply this without applying the content in it. That's kind of weird. Well, looking back at functor, there we go. This idea of an anonymous map maps a constant value on a functor. That's almost what we're doing here. It's not quite the same. And how do we do this? We fed const whatever into map. So could something like what's the type of const? Give it an A and a B, return an A. Could something like this? No, that can't be right. Can it? Going to match type K with B to B. Maybe something like that. I like this idea. Okay. Yeah. So what's happening here is we're mapping const ID onto this list. So these things no longer have 1, 2, 3. What they have is identity function, identity function, identity function. Then these two things are monoided together, and we get identity function times 4 is 4. Identity function times 5 is 5, and so on. All right, that was an interesting one. I like that. Left apply, applied discarding the value of the second argument, pronounced left apply. Remember in the last episode, I said applicative is my least favorite type class, or if I didn't say it, I certainly implied it. This kind of thing is why. As a non-mathematician, as a dilettante, I look at right apply, and right apply gives you that. Okay, 4, 5, 6, 4, 5, 6, okay. Why does left apply give us 1, 1, 1, 2, 2, 2, 3? Well, let's walk through it. Suppose conceptually we do the exact same thing that we did before. Maybe not syntax-wise, but we replace 4, 5, and 6 with ID, ID, ID. Then in that situation, 1 times ID would be 1. 1 times ID would be 1. 1 times ID would be 1. 2 times ID would be 2. And that would be 1, 1, 1, 2, 2, 2, 3, 3, 3. Why isn't this exactly the same thing? Well, for one thing, because syntactically it can't be. All right, let's try and do this. So we have our KA and KB, and we've got KA applied to, I'm going to go back and look at what I wrote, const ID functor KA. Something like that. That's what my naive brain thinks should happen. And we get a type check. Couldn't match B. That doesn't help me at all. So we gave it a KB. Well, that's what I wanted to give it. Oh. Left apply. I think I assume this would be KA, KB, returns a KB. What does that mean? That those are in a different order? Were they specified that way? They sure were. Okay, so For one thing, I'm confusing myself here, right? Because but that aside, no, I find that confusing. Why does flipping those arguments matter? Like, why couldn't this literally... Why couldn't the type signature for this be like this? Is that the same as right apply? No. Like, why isn't that valid? Maybe it is. I want to try this. KA, KB, KA, applied to, const ID, like so. And we need we actually do need something there. That's a very similar error message. So clearly there's something fundamental here that I'm failing to understand. And the first argument of apply, namely KA, in the expression, okay, so this needs to be a function. That is why my naive way of doing things doesn't work. It's because that first argument needs to be a function. Yeah, and that's in the that's in the definition of applicative, and I just forgot it right there. So that's why my naive solution won't work. Well, let's get rid of my non-solution. Let's get back to here. So we've got KB and KA. So somehow, well, what happens if we just do this? Which is literally the same solution, just with different variable names. Does not type check. Couldn't match type A with B. Expected KB, actual KA. Is that? I know this says C and not A and B, but C, A. No, that's not going to work because it's the wrong number of. Got the answer. I don't really understand why that's the answer, even though the types led me there. This is very unsatisfying. If you know, explain this in the comments, because I don't get it. It's code. It compiles, type checks, does the right thing. Feel like I don't know. Well, I'm not going to rat hole on it. I'm going to move on. Sequence is a list of structures to a structure of list. So this is the applicative version of my least favorite function, seek optional, which we had back in the list module. Let's look at it. And that's when we have this implementation, these two implementations involving folds that still confuse me quite a little bit. Well, logically, right, that was our implementation for that. So I think it's reasonable to use that as a starting point. All right. So we've got some list KA. We've got a fold. We've got something that we're going to do with the fold. Instead of starting with an optional full nil, we're going to start with something in a context. It could be anything, although they're using optionals in some of these, but they're also using exactly one and lists of lists, right? So that's also, so this is just something in a context. And then it's applied to our list, right? So this is not just a random hole. This is actually our accumulator for our fold right. So what type does that need to be? Let's find out. Okay. K list of A. So it's a list in a context. We don't have any values for that list yet, so it's going to be nil. And nil needs to be in a context, just like full nil was in a context. But we don't know what the context is, but we know that whatever it is, we can use pure to get it into that context. So now we have our whole. A and a list. Okay, so this is the type errors get hard to read when you have these contexts around. So this says some A in a we need a function that takes some A in a context and some list in a context and returns a list in a context. But since everything here is in a context, that means we really we could take that function and put it in a context. So what function takes some value and a list of those values and yields a list of those values? That sounds like cons to me. Right? Given some value and a list of values, do that. So if we just do that, that won't work because we need something that's in a context. But I like looking at the type errors anyway. Expected. Right, but so how do we get this into a context? I think we can just lift it up. And cons is a binary function. So we would use lift 2. Does not work. Why? a third argument. Well, what happens if I get rid of that? I don't see that that should work. Right? Because, okay, so this might get us a more useful error. Couldn't match A with actual type. So it's the problem is the argument to lift 2. Oh. Once again, the curse of associativity. Let's try that. That's a crazy example. Times 10 and plus 2 applied to 6 gives us, wow, that is that's something else. But we got it. All right, that's sequence. That one was, why is that one okay, but left apply broke my brain? I'm not sure. Replicate A. Did we have a replicate in the list? We did. We just used existing things to do it. All right, so there's some value, a number of times we want to repeat something. There's some item in a context. And there's very specifically a list. I see, the result is going to be a list. But they're applying this to something else. That's what I don't understand. Like if this takes yeah, I don't understand the flow here even a little bit. Replicate A4 exactly one high. Okay, so this one I feel like I understand. We're taking exactly one high, and returning a list of exactly one high, 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 high. In fact, it's almost sequenced. This one I understand. The context is outside of the list, as in sequence. Empty is empty. This is the one that is confusing me. I guess there is no context here. That's what they're saying. Okay, so what's happening here is times 2 gets applied to 5. That yields 10. They're not particularly in a context, but you can still call applicative on things that aren't in a context. But that's why there's nothing in front of, so to speak, this list here. Okay. Had to stop and think about that. Okay. Can I just lift replicate into replicate A? That would be nice. We probably can't apply replicate because replicate demands... No, it does not demand. This could be any A. Could not match type K with list. That's okay because we're in some context and I'm feeding it something not in a context. Or I'm feeding it something in a context when it doesn't have one. but can I lift it? Can I do that? Yes. Let's try the one that confused me first. Okay. Let's try this ugly boy. Replicate 3 ABC. We are not getting the correct answer. Interesting. That's the correct answer. Maybe because we're not using any applicative effect here. Do we need to actually be applying this thing? Well, not that simple, huh? Maybe this depends on, what if we used, instead of just lifting, we actually sequence this? I guess if we're using sequence, we don't need to be applying it. That's it. That one's a bit confusing. I find that composition can break my brain very easily. And I'm not sure why applying wasn't the right thing to do here, frankly. This is our last one. Filter a list with a predicate that produces an effect. Filtering exactly one, even. 4, 5, 6, not in a context, yields exactly 1, 4, 6. So the effect is, that's the effect. The effect is to put it into exactly 1. How about this one? Well, I've been chewing on this filtering one for a while, and I've tried a few different approaches. And so far, all of them are rebuffing me. I'm having trouble following the types through to the contexts that they're in. So rather than hammer on this for another hour, I'm going to chew on this for another week. And when I've thought my way through it, I will make a short video solely about this filtering example and explain how I did it. That's assuming I figure it out. If you want to give me a gentle hint, I'm welcome to take it down in the comments. I'm really glad you're joining me on this journey doing Haskell for Dilettantes. It's been easy so far, but today is the first day that I'm really feeling rebuffed by this Data 61 course. This one is breaking my brain. Well, thanks for joining me. You're watching Tea Leaves Programming. We're programming like it's 1979. Thanks for watching.